Good morning and good afternoon. We thank you for attending RheoSense's webinar, Intro to Injectability. Before we begin, I will briefly cover standard webinar protocols. First, if you have any questions throughout the webinar, please locate the Questions tab on your GoToWebinar control panel. Any questions asked will be answered by our team of application engineers who are on standby, and we will select a few to cover after the presentation with the audience. Second, the webinar presentation will be individually emailed to each attendee after the webinar. Third, a short survey will be sent after the webinar for your feedback. Anyone interested in a demo will also have access to sign up for a demo. Now, to start off, we would like to poll the audience. You will get a pop-up screen with one question. We will allocate 3 minutes for you to answer the poll, and I will now give a brief introduction. RheoSense is a leading viscometer manufacturer headquartered in the Bay Area. Our core technology, VROC, also known as viscometer rheometer on a chip, has been redefining the viscometry industry. We have a wide customer base, including leading biopharma and industrial partners. My name is Grace, and I am in marketing. Today I have my colleague David Nieto Simavia, our application engineer, who will be presenting today.
There is several motivations for us to offer this webinar. First reason is that we have some current customers that use our technology to determine injectability, and we thought it would be interesting for them to get this quick review on some additional details on this application. The second reason is that we receive inquiries on daily basis, and even more since we published an injectability tutorial on gene bioprocessing. In the tutorial, we describe the general ideas on injectability and how it can be determined in the early stages of drug development, using accurate measurements of viscosity provided by RheoSense technology. The third reason to offer this webinar is that we think our products present a number of advantages over conventional viscometers and rheometers, and that makes them a very useful tool for biopharmaceutical companies in applications where accurate characterization of viscosity is required, and such is the case of injectability. So, as Grace mentioned, we make awesome viscometers. But let me ask you first, what is viscosity? Viscosity is the resistance of the fluid to flow. And I like to think about it this way, which is actually very convenient when we are dealing with applications such as injectability. Imagine you have a piston, sort of like a syringe, and you will fill it with a very low viscosity fluid, let's say water. Then, in order to displace that fluid, you will need to apply just a small force. You will have a happy phase. Now imagine the opposite case. You fill a piston with honey, a high viscosity fluid. You will need a large force this time to push the fluid through piston. That will give you a sad phase like this guy here. Now, if we want to define viscosity in a more technical way, from a rheological point of view, we always use shear flow between two parallel plates as an example. In this mental experiment, you're going to have two plates separated by a distance d, and the bottom plate is going to be fixed and the upper plate is going to be moving at speed v1. If we are able to measure the force that is needed to apply to move the upper plate at that given speed, we are set to establish the viscosity through this kind of flow. We're going to have the shear rate, which is given by the velocity of the upper plate divided by the distance between the two plates. And we are also going to have the shear stress, which is given by the force we measure divided by the area of the upper plate. The characteristic shear viscosity of the fluid is given then by the ratio of shear stress to shear rate. Measuring shear viscosity becomes tricky because shear rate is only well defined for a few geometries, such as cone plate, parallel plate, circular slit, and rectangular slit. If you're outside these geometries, you are not going to be able to establish shear rate accurately. And what you will get is what commonly we refer to as apparent viscosity or index viscosity, which is useful to compare the viscosity of several fluids or to order them or index them, but not to establish the true property of the material. RheoSense BROC technology, which stands for viscometer rheometer on a chip, is based on a rectangular slit geometry. So shear rate is well defined, and among other advantages it presents, it measures absolute viscosity or true viscosity. Additional advantages are the smallest sample volume in the market, a wide dynamic range in terms of viscosity and shear rate, and fast and superior accuracy and repeatability. So how does BROC work? BROC is a hybrid of microfluidic and MEMS technologies. Basically, we put together a microfluidic channel with a pressure sensor array. As the fluid flows through the channel, we characterize the pressure as a function of position. Let's take a closer look. We have our rectangular slit microchannel with the pressure sensor array at the bottom wall. We impose a flow rate, and since we know the dimensions of the channel, we are effectively imposing a shear rate. We can also measure the pressure as a function of position, shown in the figure here. Using this information, we characterize the pressure drop through the channel, which is going to be proportional to the shear stress. Finally, we put shear stress and shear rate together to obtain viscosity. Powered by BROC technology, RheoSense has developed a family of products for the measurement of viscosity. There are two main branches. The first one, corresponding to MBROC, presents extended capabilities, and we like to think about it as the R&D branch of viscometers. MBROC offers the smallest sample volume viscosity measurement in the market. It also presents a very wide dynamic range in terms of viscosity and shear rate, and has temperature control capabilities between 4 and 70 degrees C. MBROC has two siblings, EVROC, our extensional viscometer, which we will not cover today but will be the subject of a future webinar. And additionally, we recently developed HTS VROC, which stands for High Temperature High Shear Viscometer. HTS VROC has the same specifications as MVROC, but it has been modified to withstand higher temperature conditions. The last member of the family belongs to our QC branch. Microvisc was developed as a portable viscometer. It requires a slightly larger sample volume and presents a reduced dynamic and temperature range, but in exchange for its low weight and size and disposable pipettes. This family of products have made us a market leader in biopharmaceutical applications. We have collaborated with our customers in applications such as protein, RNA, and antibody therapeutics, protein formulation and stability, accurate viscosity characterization to help particle sizing through dynamic light scattering, and injectability, which is the topic at hand in this webinar. Let me introduce the topic and define what we mean by injectability. Nowadays, the trend in therapeutics is to reduce the frequency of dosing. We're going to achieve that increasing the concentration of the active compounds in the new drug formulations. The increase in concentration is going to lead to an increase in viscosity. There is a number of features that are going to be relevant for injectability. We're going to have a range of interest for both concentration and viscosity for the therapeutics. Within that range, there is two very important effects. As we can see in the figure, first, viscosity is not only dependent on concentration. It also depends on the specific therapeutic in the formulation. Small changes in the active compounds inside the drug can have significant effects on the viscosity. Second, for a given formulation, after a given critical value for the concentration, the viscosity of a solution is going to increase almost exponentially with concentration. Those two effects, and a third effect regarding the dependence of viscosity on shear rate that we're going to discuss later, are going to be the key parameters in an injectability study. So how do we establish injectability? Injectability is determined by the force we need to apply to the plunger in a given syringe and needle to inject the fluid into a patient. This force is going to have two components: the piston friction with the syringe walls and a resistive force due to viscosity. This second term can be separated as a pressure drop due to viscosity times the area of the plunger. For a Newtonian fluid, as in the example shown in this figure, viscosity is going to be independent of shear rate. For this kind of fluid, the flow inside the barrel and the needle is going to be described by Hagen possible solution to the fluid conservation of momentum. The resulting pressure drop in a circular tube is going to be given by this expression. We will have two components. First, the pressure drop in the barrel, and second, the pressure drop in the needle. However, since the radius of the barrel is much larger than that of the needle, we can neglect the barrel contribution. We are left with the pressure drop that is proportional to viscosity, the needle length, the flow rate, but inversely proportional to the 4 power of the radius. We will use this pressure drop to estimate the force we need to apply to make our therapeutic drug flow into the patient. However, it is important to understand that to apply Hagen possible pressure drop, we need to determine that our fluid is Newtonian, and we need to do so at a shear rate that is relevant for the injection process at the needle. In order to achieve that, we need to measure viscosity over a wide range of shear rate. Few viscometers allow for high shear rate measurements because the large length scale of their measurement chambers leads to flow instabilities at high Reynolds numbers. RheoSense V-Rock technology, small scale, results in low Reynolds numbers and allows for viscosity characterization at very high shear rates that are required for injectability studies. So using the expression for the pressure drop, we'll be able to estimate the viscous component of the injection force. And here we have some examples for a 29 gauge needle and a couple of injection rates that corresponds to these shear rates. If we have a viscosity of 30 centipoise, the estimation for the injection force based on the pressure drop equation we just present is given here. As you can see, we do pretty well, and the small differences observed are most likely due to the fact that we are neglecting piston friction. Note that the injection rate that is relevant for a specific application is going to be strongly dependent on the size of the needle. As you can see in this table, with two different gauge needles, we cover a wide range from 36,000 to 220,000 inverse seconds. And we need to be able to characterize viscosity at these large shear rates. So now, what happens if in fact we do have a non-Newtonian fluid? A fluid or a formulation where viscosity significantly depends on shear rate. We are commonly going to have the behavior exemplified by the red line in this plot, where there are three well-differentiated shear rate regions. A first region at low shear rate, known as the zero shear viscosity plateau. A second region from intermediate to high shear rates that is often well described by a power law. And last, a second plateau region at even higher shear rates. In the region where viscosity is dependent on shear rate, the velocity profile is no longer parabolic, as it's exemplified by the blue and red lines in this figure. The slope of the velocity profile, which is the shear rate at the wall, is no longer described by Hagen-Possible law. It is larger. In order to estimate the shear rate, we need a constitutive equation for the fluid behavior because we need to measure viscosity at the true wall shear rate for accurate estimation of injectability. Based on the apparent shear rate, we can apply the well-established Weissenberg-Rabinovich-Mooney correction where we basically use the measurements of apparent shear rate and shear stress to recalculate the true shear rate. Once we have the true shear rate, we can use the definition of viscosity to recalculate the now true viscosity. Now, we can get back to our non-Newtonian therapeutics. I'm showing here two examples of the viscosity as a function of shear rates. As you can see on the left figure, for monoclonal antibodies, the rheological behavior is going to depend on concentration. This is very important because based on experience at lower concentrations, you might think that it is enough to measure viscosity under, let's say, 1,000 inverse seconds. While, as it is shown here, your viscosity can start to decrease, your fluid will start to shear thin at higher shear rates. That will result on a large overestimation of the viscosity at the shear rate that is characteristic for the injection process, which will result in a large overestimation of the injection force. To a good approximation, we are going to assume that a power law can be used in the shear thinning region. For this constitutive equation, the viscosity is proportional to a constant times the shear rate to the power n minus 1 power, where n is the power law coefficient. So you will have n equal to 1 for a Newtonian fluid and n below 1 for shear thinning non-Newtonian fluids. Once our constitutive equation has been established, we can obtain a solution for the flow inside the needle, and the slope of the velocity profile, the shear rate, is going to be given by this expression for a power law fluid. Notice that n, the power law coefficient, appears here in the denominator. This is going to result in the same shear rate as for hanging possible flow for n equal to 1 Newtonian fluid, and in larger shear rates for lower n in non-Newtonian shear thinning fluids. Once the shear rate is known, we can use our viscosity measurements to establish the viscous contribution to the injection force. This is a flow chart presenting the very simple steps you will need to follow to establish injectability. First, you need to measure viscosity from low to high shear rates, ideally covering the shear rate up to the needle injection rate. Then, if your fluid is shear thinning, you can feed a power law to obtain the exponent. With that, you can calculate the wall shear rate and use the power law to estimate the viscosity at that specific shear rate of the wall inside the needle. If you put those two together, we can obtain the viscous contribution to the injection force, and we're set. So we're going to give some examples for the injection force calculation for non-Newtonian fluids. We have kept the Newtonian example on the top of the slide to point out that the piston friction contribution is going to be small. We're presenting three fluids. First, a Newtonian fluid with n equal to 1, which is in blue in the figure, and then two shear thinning fluids with n equal to 0.8 and n equal to 0.5 respectively in green and red. Our calculations are going to be based on a 29 gauge needle and an injection rate of 0.1 milliliters per second. First thing we can notice is that the non-Newtonian behavior of the sample is in fact going to result in higher shear rates of the wall for the same injection rate. At those shear rates, the viscosity of the non-Newtonian fluid is going to be much lower than the Newtonian counterpart. This is going to have a tremendous effect in our force estimation. Again, if we have measured our viscosity at a low shear rate, and based on this measurement only, we have calculated the injection force necessary to make the fluid flow, we will have overestimated the force by 50 to 60% respectively. This kind of error or mistake could result in the rejection of a drug or therapeutic that will be otherwise considered injectable. And this is the real importance of the analysis we have presented here today. With that, I would like to summarize some of the important advantages that our system presents over some conventional methods to determine viscosity. We have a very small sample volume, the smallest in the market. We provide measurements of viscosity that is true, is not apparent, or index viscosity is independent of the instrument, independent of the geometry. We have high shear rate capabilities, a very wide range of viscosity measurements and shear at the given shear rates. And we would like to thank everyone for joining the webinars. We would like to thank our customers for their support. And now we will respond to some selected questions from the audience. Thank you. We have a first question asking what are the FDA limits for drug injectability? As far as we know, there are no FDA limits for drug injectability, but there are some practical limits, as you can imagine. Automated injection systems can only apply a certain amount of force, and during manual injection as well, only so much force can be applied before causing discomfort, meaning that high viscosity materials or fluids will take much longer to inject, and that will lead to another type of problems. We have second question. Is the true viscosity concept being accepted by FDA? Well, true viscosity is not a new concept. We just the true part is just added to point out that that's the actual viscosity of the sample. That's the material property that it should be independent of the system that you're measuring with. So just pointing out the difference with an index or an apparent viscosity measurement. And as such, it does not require specific acceptance by the FDA. Next question, do you have data in support of a correlation in viscosity results between the cone and plane rheometer and MB-ROC for protein solution, or specifically in monoclonal antibody solutions? We do have data supporting the correlation in viscosity against cone plate measurements in systems such as Shanagam and other systems. We can provide reference for a couple of studies in monoclonal antibodies where there has been a good comparison and correlation between MB-ROC and rheometer systems. Next question is, what add-ons do we need on the existing MB-ROC to be able to do a sweep of shear rates from 0 to extremely high shear rates? Well, for the low shear rate or flow rates, the following are required. You will need 100 microliters to 500 microliters syringe with the corresponding jacket and a chip capable of measuring the sample under low shear conditions. Assuming the viscosity of your sample is pretty low, from 1 to 100 centipoise, an AO5 type of chip with a 50 micron channel depth is typically ideal. For high shear rates, the following will be required. You will need a 1 ml or 10 ml syringe and jacket, and a chip capable of performing these high shear measurements. As an example, an EO4 chip with 40 microns channel depth with a 10 ml syringe will be capable of performing measurements from 100,000 inverse seconds to 1,400,000 inverse seconds for a sample that will be between 1 to 30 centipoise. Next question, can you restate what's the true viscosity about? Okay, so true viscosity is a term we use to describe values that are instrument independent. That's to say, if you test sample A at 100 inverse seconds using one instrument, you should see the same viscosity that if you use another different instrument. For non-Newtonian fluids, this requires proper characterization of shear rate, since the viscosity depends on shear rate. And that proper shear rate is what we'll call true shear rate. That the fluid experience is actually experienced inside the test chamber that you're using with your measuring method. Calculating that shear rate is more complex for non-Newtonian fluids than for Newtonian fluids. Only certain viscometers and rheometer geometries have a fully characterized shear rate that allows us for this true viscosity measurement, as opposed to apparent or index viscosity, which is helpful to order materials or fluids in terms of their viscosity values, but it doesn't give you this consistency between measurements. And last question is, can I get the slides? Yes, the slides of this presentation, as well as the recording, will be released shortly after this webinar, and they will be available at RheoSense website. Uh, with that, I would like to again thank all the attendees and all the people signing into the webinar. Thank you very much. We hope to see you in our next webinar that will discuss some of the basics of viscosity measurement and Newtonian versus non-Newtonian fluids. Thank you very much. Bye-bye.